Thank you for enduring our extended break. I promise you'll not have to cool your jets that long the rest of the afternoon, rest of the day. So we're going to start our first panel discussion of the session. If you haven't been paying attention to the Purdue University 150 celebration, they have 4 major themes of research for the next 150 years. And we've structured our panel discussions around those 4 themes. So the first of the 4 we're going to talk about is artificial intelligence. And I'm delighted that our moderator today is Professor Jennifer Neville. She's a professor of computer science and statistics here at Purdue University. And she has been involved with over 100 peer-reviewed publications, 5,000 citations, focused on developing data mining, machine learning techniques, and complex network domains, social, information, and physical networks. There's not much she hasn't touched, and she was clearly our first choice to moderate the AI panel. So with that, I'll introduce Jen and let her introduce her panel.
Okay, thank you. Is this going to be a problem with 2 mics? Like, should I turn? No, it's fine. It's fine? Okay. Well, thanks everybody for coming. I would like to introduce our panelists here for our discussion on AI and security. Let me see if I'll go from the farthest with Dr. Chris Clifton, is a professor of computer science at Purdue. He works on issues related to data privacy. I'm sure you all know him because he's always here at every CERIAS symposium. He has been a sort of stalwart member of both the security group and the data mining groups here at Purdue in computer science. He left for a little while, from 2013 to 2015, to serve as program director at the National Science Foundation. And prior to joining Purdue in 2001, he was a principal scientist in the Information Technology Division at MITRE. And before MITRE, he was a professor at Northwestern University. So who's next? We have Ashish Kundu. Dr. Kundu is a master inventor and research scientist in the security research department at the T.J. Watson Research Center at IBM in New York. He received his PhD in computer science from Purdue in 2010, and his main research interests are broadly in the area of cybersecurity, privacy, compliance, and AI ethics. He has led the security and compliance group at IBM Watson Health as well as IBM Watson Education. And his work has led to more than 100 patents filed with more than 80 patents granted, and he has more than 30 peer-reviewed academic research publications. He has been recognized with the honor of Master Inventor by IBM Research, and while he was here at Purdue, he received the CERIAS Diamond Award for his outstanding contribution to PhD research in cybersecurity. And he also got the Best Graduate Teaching Assistant Award. So next, okay, now I'm in the right order, so is Mr. Paul Conoval, who is Director of Technology for Northrop Grumman's Mission Systems Sector, and he's a member of Northrop Grumman's Corporate Technology Council. In this role, he leads a wide range of advanced technology initiatives, including integration of the sector's R&D program, university research, intellectual property, innovation, and development of emerging technologies applied to intelligence and DoD. His prior work includes development of national scale intelligence, SIGINT, and communication systems with an emphasis on information theory, digital signal processing, and electronics hardware design. Mr. Conoval holds a BSE from the Cooper Union School of Engineering and an MSE from Rutgers University. And then finally, last but not least, we have Dr. Sanjai Narain, who is a fellow and chief scientist in Information Assurance and Security Department at Perspecta Labs, which was earlier called Vencor Labs. And then he also has been at Telcordia and Belcor. Currently, he's a principal investigator of 2 DARPA projects. One is on configuration security, and the other one is on design space exploration for cyber-physical systems, such as underwater robots. He also leads a science of configuration project to synthesize error-free network and cloud configurations in minutes rather than months. All of these projects leverage 2 branches of AI, machine learning and deductive reasoning, and he has his PhD in computer science from UCLA in 1988. Okay, great. So now that I have introduced everybody on the panel, I'll tell you a little bit about the format that we'll have here. So I'm going to open it up for each of the panelists to give a 4 or 5 minute statement on their views of what are the main opportunities and challenges that we face with respect to cybersecurity as we move into this new age of AI. So really the advances in cyber-physical systems and AI have led to what people refer to as the fourth wave of the Industrial Revolution. Obviously, these kind of systems are being embedded throughout the fabric of our lives, and thinking about how security sort of intersects with AI is a very important topic to talk about, not only from the viewpoint of how we can use AI to improve security, but also how do AI systems offer new challenges and security risks that we have to deal with. And so once each panelist gives their opening statements, then we'll open it up to questions for the audience so we can have a good discussion. Okay, so maybe we should start with Dr. Sanjai Narain, because he has a couple of slides that he wanted to show to set the context here. Are they showing? No.
Step over with you because I want to pull something up as well. Start off.
Okay. So you can hear me, right? Okay. Right. Thanks a lot, Professor Neville, for the introductions. I will be talking about the application of AI to security. There is a lot of work on securing AI, but I'll be talking about the other side of things. So I am the PI of a new DARPA project and the new program called Configuration Security. And there the problem is that these IoT infrastructure is being built with much larger number of devices than the 40,000 routers that was mentioned earlier, Ray Rothrock's talk. And configuration errors, it's well known, well documented that they account for about 80% of your downtime and vulnerabilities. And that's going to be even worse a problem for IoT. So the configuration security program is to figure out what to do about it, how to eliminate configuration errors ideally. But they are posing a somewhat, well, this is my opinion, that somewhat easier problem than, because eliminating configuration errors is an open-ended problem, is so to minimize the attack surface, the configuration attack surface. That is, can we give just enough permissions to the devices so that their job is done, they can do their job. So that's why they want to minimize the IoT configuration attack surface, but while preserving functionality, right? Preserving functionality is important because if functionality is not important, then you switch off all the devices and no cyber attack is possible. So, my project is on applying AI techniques to solve that problem. And there are a couple of interesting and thought-provoking reads in this area before we try to apply AI. One essay is by Keshav Pingley at UT Austin. He says the unreasonable ineffectiveness of machine learning in computer systems research. So he is underwhelmed by all the progress of AI to computer systems research, which would, I think his area is programming languages. And so what he's saying is that while there have been some interesting applications, but there is nothing mind-boggling like self-driving cars in urban environments. So he wants to have the equivalent of that. He hasn't seen that. But he does give some ideas as to what that would mean. And the second somewhat sobering article is by Robin Sommer and Vern Paxson, called Outside the Closed World on Using Machine Learning for Network Intrusion Detection. And the idea is that this whole concept of making a machine learn normal behavior and then using that to detect abnormality and therefore the detection of a zero-day attack, they are skeptical about that whole thing because machine learning requires both positive and negative examples for it to be effective. So if you just give it positive examples, then it may not work. So science advances by producing counterexamples to conventional wisdom. And so we are trying to apply AI in the following way. When you say minimize IoT configuration attack surface while preserving functionality, this seems like an optimization problem, right? All the optimization engines, they solve exactly this problem, minimize or maximize an objective function subject to constraints. So if you can cast this problem as an optimization problem, then we can use very off-the-shelf, very powerful optimization engines like, have you heard of Cplex and systems like that? So let me sketch to you how we are trying to do that, what our approach is. So next slide, please. OK. So one of the central ideas is that of a scoring function. And this is related to the resilience score that Ray Northrop was mentioning. So given a configuration of a system, can we give a score to it as to how vulnerable it is, and then whether it can deliver the functionality or not? This is like a building code. So you build a building according to code, and then no matter how subject to constraints, that regardless of how the stresses are placed on the building, it's going to deliver some functionality or some assurance properties. So similar idea. And so the critical thing is that we are not modeling adversary behavior. We are only looking at the configuration and scoring it according to functionality and vulnerability. And then we model the attack surface as an objective function on these scores. So and then the functionality requirement is just a predicate on these scores. And now we can use the existing optimization engines. Now the critical question is, how do you figure out what the scoring function is? So that's where AI comes in. We can learn this function through simulation. So we have a system, and simulators are available. So we drive it with lots of different configurations, and we evaluate the scores. And then we collect the training data, and we pass that to a neural network learning engine and produce a neural network. And then a neural network can be converted into a mixed integer linear program. How many of you are familiar with that idea? OK, right. So one. So this is not commonly known, but it's actually quite well understood for people who do verification of neural networks. So neural networks, of course, with the activation function we call ReLU, rectified linear unit, which is quite powerful. So you can convert any neural network with ReLU into an MILP. And now you can use the, you learn the scoring function as a neural network, hence an MILP, and then you formulate your objective function, and then you can use an MILP solver to produce a configuration that minimizes the attack surface and preserves the functionality. So we are not modeling the adversary behavior, and yet we are able to solve the inverse problem, that if you're given a, so now you can say, I want a configuration given this score, so the MILP solver will produce that for you, because it does not make any distinctions between input and output variables. There are only constraints, so it just solves that constraint. So you can solve the inverse problem. You have a resilience score, for example. You want to say, OK, how should I know my system has a bad resilience score. Now, how should I reconfigure my system? So this approach could attack that problem. So that's what I have to say. Thanks a lot.
OK, thank you. Paul, you want to go next?
I think you're pointing at me.
Yes,
so
yes, go ahead, Paul. Yes, thank you.
OK, so anyway, from a different perspective, so Northrop Grumman is a large-scale systems integrator. And the biggest problems that I perceive in this whole domain is the convergence of cybersecurity, artificial intelligence, advanced analytics is really changing and creating a whole new paradigm on how we conduct cyber operations. And adding to that, the ability to build autonomous systems, that require near real-time dynamic decision-making in an environment that we don't really understand what all the attack surface and all the possible defects are, and we have to create mission-critical systems. And so one of the things I do, I work with a joint collaborative industry-government technical group sponsored by the AT Association, that's the Advanced Technical Intelligence Association, and with the Office of Director of National Intelligence, ODNI. Some of you might have heard of the INSTEP program, but that's the Intelligence, Science, and Technology Partnership. So when we get together, we ask questions like this, across the industry, what are our biggest problems? And when you deal with large systems, so our biggest problems, I believe, are very large-scale heterogeneous systems that cross multiple domains that have to operate in chaotic environments, whether it's a wartime environment for military systems or if it's a humanitarian relief operation and so forth. And you're operating across boundaries of thousands of different nodes, of different modalities, of extremely high volumes of data that has to be decided on very quickly. Now, part of the problem is that decision-making in a very sensitive operation can't be done autonomously. You have to do it with the final approval of a commander or a human decision-maker. So if you think about the ability to how humans would interact with machines in the context of being secure in a cybersecurity sense, that changes how we operate. So one of the things that we're sort of working on with this collective community is understanding what the right level of cybersecurity is to accomplish the mission objectives and the right level of AI. So going into any new forum, I think one of the biggest issues from the first 5 seconds is defining a taxonomy that we all agree on across the board. So now, just as a case in point, Northrop Grumman is a large company, so one of our sectors builds unmanned vehicle platforms, a Global Hawk. This afternoon, I'm actually on the agenda to present, so I'll have some videos and some graphics of it. The information systems sector, which became mission systems sector, is building large-scale enterprise systems. So now when you go in and say, what do you mean by autonomy? The aerospace systems sector is going to talk about, unmanned airborne autonomous vehicles. When you ask somebody from the information technology domain, they're going to say large-scale network enterprises with software-defined networking that could resiliently reconstitute communications against cyber threats. So the very same question and the very same nomenclature, autonomy, means a whole different thing. So the idea of effective mission operations also implies what we really need to do for mission objectives, and cybersecurity could mean something very different if you put a mission context around it. So in other words, if you say we have some sort of military campaign that's going to last for half an hour until we take out some threat, then security only needs to last a half an hour. It doesn't have to last for all archival storage time. So then that changes the methodology, it changes the mathematics, it changes the algorithm, it changes the concepts of operation. So without the context of what we're trying to do with our operations and our large-scale systems, it's very hard to talk about what the right cybersecurity solution is and what the right artificial intelligence, machine learning enabler would be to help achieve those goals. So anyway, so that's the whole thing, the operationalization, the whole conceptualization of how you incorporate AI, cybersecurity, advanced machine learning within a mission context, and then the whole ecosystem that goes along with it in terms of how one does designs, how one does validation, how organizations do post-auditing of results. And it's a continuously regenerative cycle, and it's not one solution. And on a chaotic campaign where something is happening in near real time in a chaotic environment, the dynamics are really in terms of seconds and minutes and not years and decades. So I'll pass off the microphone to you.
Let's give Paul thanks for that.
Good morning, everyone. Can you hear me? Right. So, if we look at the trend over last several decades in computing to today, what is happening is on one side we have data and knowledge, the other side we have computing, but now there is a tipping point that has come up about intelligence. So you look at the whole triangulation about it. We are moving in the direction of we're really excited about intelligence, right? What can we do with intelligence, which is artificial intelligence? I remember when I was an undergrad in a top school in India, one of my professors asked, "Why do we need AI, artificial intelligence?" And it was a tough question to ask that time. There are several answers, tough answers. There are several answers to it, but now the answers come very, very easily when you look at another dimension of what we produce out of these three triangulated attributes. Right? We have data centers, huge data centers on one side of the spectrum. We have IoT devices, very miniaturized IoT devices on another side. And what we are also building, cyber physical systems which are mobile, like autonomous self-driving cars. Right? If we look at all these two different trends happening in the whole area, it is really leading us to think that that there is a real need for moving in this direction of artificial intelligence and machine learning, but is security still needed? And I remember when I graduated from computer science and CERIAS and joined IBM TJ Watson Research Center, one of the tagline I posted there in my door is that security is a new functionality. And I think at some point we are already thinking security is the new functionality. Intelligence will totally be, today as a human being, right? We always think about our safety and security, right? Most of our intelligence goes about protecting that, protecting the data, knowledge, and the materials we have acquired. So security is the new functionality. It will continue to be, whether it is AI, quantum computing, whatever not it is. So therefore, it is a great pleasure and honor for me to come back here as an alumnus and talk about it. Now, if we look at what are the threats, right? The threats are, the threat landscape is changing a lot. From academic scenario, the threat landscape is basically highly sophisticated and complicated in terms of coming up with new cryptanalysis attacks, adversarial machine learning, as well as, for example, membership attacks, breaching privacy of machine learning models and training data. But if you look at real world scenarios, right, it is the weakest link in the system still is the problem. Weakest link, you look at configuration problems, right? The databases, you look at Experian, right? They talked about the database password was default. There are so many, recently there was hard drives. Shodan is a IoT search engine, okay? And you go there, you can search for hard drives, SCSI hard drives, which are available on the internet with no authentication required or default authentication required, right? So the weakest link is not essentially the highly evolved threat landscape. It is the configuration, the programming language artifacts that we are not giving out time to. I'll give one example here that I did, since there are many students here, to encourage you not to just think about complicated attack scenarios, but also think about how do you break into a system, okay? And then think about building a technology from that side. That will help you a lot. In 2010, after my internship, I learned that C++ has a vulnerability called, has a construct called placement new. And placement new can be used to carry out whole lot of buffer overflow attacks. I thought people might have discovered it already. It has been 2 decades or more the buffer overflow has been talked about. Interestingly, there was not a single paper talking about placement new attacks. I wrote a paper, went into a top conference, and then GCC released a patch on that, right? Still there are many more things to be done. So I would encourage all of you to, while taking a look at really complex attack scenarios and technologies to develop around cybersecurity, look at in real systems what are the issues and build around it as well. I think I'll pause there. Thank you.
Okay, I'll take care of it. Okay. Let me drive. I'm going to be the curmudgeon. I come to this out of the data mining, machine learning community database, dealing with the information first and then moving towards security, and point out the difficulties of using AI in security. AI, machine learning techniques are very good at discovering general truths, discovering things that apply most of the time. In security, often what we're fighting against is an adversary who's finding that one little weak spot. That, that little niche where you can get things through. Most of our system is secure, can't break in. And if we're not careful and we try to apply machine learning, that's what we get. Most of our system is secure, just like it is today, but there's going to be those few little holes. There is an area of machine learning known as adversarial machine learning. A lot of that work has been, how do we develop techniques to break machine learning? And they're becoming very effective. Also techniques to protect against that. And I got to thank Paul and Northrop Grumman. There are several of us working on this area, collaborating with Northrop Grumman, specifically on how do we defend against these attacks. I'm sure many of you have seen a very visible one, which is a stop sign. That people put some stickers on the stop sign and all of a sudden these image recognition systems see a speed limit sign. We as humans don't, but that AI, they've found a little weak spot in there where it's completely off. That said, there are ways where we can use AI, machine learning techniques. We have to just be very careful about thinking about what they do for us. And I will say this is something that CERIAS has been very active and very involved in. And just to give an idea, this was a CERIAS seminar, developing custom intrusion detection filters using data mining. This is a seminar talking about using machine learning techniques, but what we did in this was looked not at developing completely autonomous systems, some system that's going to find things for us automatically, and we don't have to worry about how it works. It was to help us as humans to sift through things, to go through and say, here's the things that you should, that it looks like you can safely ignore. Let's develop some human vetted rules to quickly build intrusion detection systems. For those of you who haven't figured it out from the picture, notice the date when CERIAS was looking at things like this. Almost 20 years ago. So you're in the right place for this. And in fact, do we have any CERIAS alumni from around that time? This was a course offered in 2001, looking at using machine learning techniques in security. So this is nothing new for CERIAS. I want to point out we've been thinking about this for a long time, making a lot of progress, but we have to be very careful. Many people who get into machine learning today look at this wonderful technology that just seems to solve all these problems. People think of this as pointed out. A lot of people, Sanjai pointed out some papers who looked at this as, well, you just get training data, you go through your training data, and first thing he points out is, we don't have good negative examples in the training data. We don't have we've got kind of one class for most of our examples. Yes, there's machine learning techniques that deal with that. We need to understand what they do and not just blindly assume that this new technology is going to solve all our problems. So anyway, on that note of being a bit of a curmudgeon there, I'll finish off and turn it over and we can get some questions going. So.
I guess maybe, I don't know if people have questions already teed up to ask people. Okay, come on up. I was going to throw in the first question, but I will hold off.
Is it?
I think it's on now.
Hello?
Yeah.
Yeah, we got you.
All right. So my question, when I ask this question about security, I'm thinking about public safety, not necessarily about cybersecurity. So my question is on AI, thinking about, it seems like we might not have a handle on the right applications for AI. So my question, as a scene setter, what do you think about AI projects like Project Maven, where Google was using AI potentially to help the Defense Department with potentially lethal actions? What is your opinion about the ethics of AI, if you could comment on that?
Go ahead.
We are actually, that's a great question. So if you look at AI, security, privacy, compliance, they lie on one side, and then you have safety and ethics, they lie on the other side, right? And they are not independent sets. They're essentially, there's a lot of intersection between them. Playing in their complete intersection, the sweet spot, is always what everybody would like to work on. I'm sure you must have seen that there has been a lot of discussion about AI ethics. For example, from IBM Research, a couple of years back, there was an AI ethics white paper that came out. In fact, I was contributing to that as part of the board. Recently, Google started an ethics board and they dissolved it. But the challenge is that ethics is highly context-oriented, right? And when you solve a problem with AI, right, then the challenge is about how do you protect it, right? And protection is something not that, it can be context-oriented, but it may not be aware of what the cultural requirement. Ethics can be culturally driven. Ethics can be driven by who is the adversary and who is not an adversary in a military area, right? So I guess there's a role of game theory there, to learn and preserve the ethical models of ethics and safety in terms of utility functions, and apply that while you provide a game theoretic model of cybersecurity for ethics.
Yeah, so a couple of comments to that. So yeah, I'm familiar with Maven, and now so I consider a dichotomy, right? When we talk about AI, so I like to think of one side of it's physics-based AI, and the other is human AI. And what I mean by that is, as I said before, I get pretty good visibility over a wide swath of technologies, so nanotechnologies all the way up to big systems. And we're using machine learning and AI just to compute optimum coefficients of waveforms for more effective radio communications for improving bandwidth efficiency. Okay, so there's no human factor there. You have noise in the environment, and you have to make sure you handle the variabilities of signal noise, all the impairments that you might experience. But then when you get to the human side, that's when you have the nonlinearities. So you have like intentional activities to circumvent your algorithms or come up with something that will compromise the ability to be secure. So when we deal with, so when we generally speak about is AI ethical or not, I think it depends on how it's used. And we do spend a lot of time needing to understand the policies, the governance, the legal aspect, the privacy concerns, and only apply the AI that meets all those conditions. And that's one of those constraints of actually making AI practical in government military systems. So, so how we would use it is, say, decision support. So decision support is sort of an offline activity that you could do anything. You could do gaming, you could do concept of operations, you could do campaign, task planning and whatever you want to do. And then you use that to take the results, and ultimately the human is going to factor in what pieces are aiding the human and which pieces that the human actually has to take over to make those final decisions. So now our adversaries, on the other hand, might not follow the same list of governance, ethics, compliance, and so forth. And that sort of puts us at a disadvantage in terms of speed in which an attack occurs until the time we could recover from the attack, especially if what we're using machine learning for divulges privacy information of individuals. So you have to, and we do have research in the area, privacy preserving, information sharing, and attribution has to take into account all the policy and ethics. So it's not a simple answer, but we are fully aware of it, and the constraints forces us to work around some of these things that we could be more efficient with AI. We have to find other means of doing it.
Oh. Go ahead,
Sanjai.
Sanjay.
So I don't have any, I haven't thought much about the ethics aspects, but I was recently at a DARPA AI colloquium, and there was a very, very interesting panel discussion there. And that's the reason I got up to get my laptop and look at my notes. And I mean, by the way, talks are there online. I'll be happy to give you the link. But a couple of points they raised was that AI could be used in the legal system. Judges, their sentencing guidelines or judgments and all can sometimes be clouded, and then AI could help to eliminate some of that bias that people feel. And then there were other questions raised, like, suppose that the autonomous cars are quite robust, the amount of errors they make are, far lesser than humans, but then would you be rather killed by an autonomous car or by a human driver? These are some of the questions that they were raising.
Okay, Chris.
Yeah. And I'll point out one other thing, and this is a great question, but one of the difficulties here is we are using these AI systems to solve problems that we have a hard time solving as individuals, as humans. Which means often the way they're solved, we don't fully understand. And many of the AI techniques are rather opaque. Explaining actually what they do is very difficult. Justifying what they do may be a little easier, saying, well, here is a possible explanation. It may not actually be what really happened, but it's a reasonable explanation of what could have happened. We tend to accept that for humans, for explaining our decisions. But another thing that comes into the ethics is, and is touched on, bias. We think, okay, well, these will help reduce bias. But it turns out these systems can introduce bias, even where there was no bias to begin with. And you mentioned an autonomous weapon system. Well, what if we train that and teach that system to avoid avoid killing civilians? And we look around and basically we gather all kinds of pictures of civilians and military in the midst of civilians and such here. And then we deploy that someplace else where the dress, the likelihood that somebody's carrying a walking stick that might look like a weapon may be higher. And all of a sudden, it's making really strange determinations of what is a civilian and what is not. So we've kind of tried to put an ethical behavior into the system, but it turns out not to work the way we expected. This, I think, is a big problem with ethics in AI, is that how these systems are going to behave in practice is very challenging. And this is particularly challenging in these public security type of systems where we don't have a lot of chance to try them out and see how they work and don't work in practice before we're using them for real and they may make mistakes. So that's I think a big concern. Yeah.
So somebody might say that, okay, if the AI system, humans are they make large numbers of mistakes. So if the AI can introduce, drastically reduce that error, sure, they'll still, get the wrong guy, but would that not be preferable to the current state of affairs?
Sure.
So I think we could discuss this question for the entire hour. So maybe let's move on to let someone else come in with a question. Great.
Excuse me. It actually ends up being a follow-up to Mr. Clifton's comment. I find it very, very disturbing that when you put the stickers on the stop sign, what failure mode you get. You would think if an AI looked at a sign the way a human or other animals do, you might say, oh, well, it thinks it's a hospital sign, or it thinks, that that's a no U-turn sign. But instead, say it finds a kitten, or there was another one that came out recently about they had a picture of a room, you put an elephant in the room, and then the AI started thinking like the couch was the end table, and the end table was a floor lamp and all that. It's not picking things up the way that we would pick it up. And what I'm wondering is, do we need to develop, especially the neural networks, ones that actually can explain themselves? Coming from doing some expert systems in the past, it's very disturbing to me to think that, okay, we're just going to throw a bunch, it's like the old Sidney Harris cartoon where you see big equation, then a miracle occurs, then the rest of the equation, and one scientist saying to another, I think you need to be a little more explicit here in step 2. And I kind of feel like what we're concentrating on in AI right now with the neural networks, we feed a bunch of training data in, and we're hoping a miracle occurs, that it will recognize the things we want it to recognize.
So can I sort of respond to
Sure,
that
yeah.
a little bit? So from a practical point of view, yeah, so I agree with all that. We've all seen the extreme of a stop sign looking like a, whatever, yield sign, or the ability, if we can't understand something, so that's the whole issue of explainability, which is one of the key problems. Getting confidence in the autonomous decision making by a non-human, gaining that confidence, and then the explainability is important. So often what will happen, you can end up with an optimal solution based on unexplainable events, and then we won't accept that. We'll back off the optimal solution to be suboptimum until we get to a point of comfort that we could explain it, at least to the degree of confidence enough to carry on whatever we're trying to do. So what that would mean is that this whole scale of confidence, explainability, and how much explainability versus the impact and the unexpected behaviors or emergent behaviors that might occur. So we, as a practical, an analyst that's doing intel analysis, for example, will use AI to reduce the workload for the analyst, such that he'll see the stop sign and he'll see all the other symbols and other signs that he's supposed to. So a human analyst could weed those out very quickly. If we rely 100% on an AI, then you're going to be subject to a lot of false hits and a lot of adverse impacts. So the ability of an analyst, so that's the practical side of it. So you do enough AI, just enough, so the analyst's workload could be reduced so they're effective with the less workforce. You have the correct targets that you identify, whether it's intel analysis based on documents or it's imagery or whatever. So you'll keep scaling that back. And also you take into account the fatigue of an analyst. And where an analyst a human analyst starts becoming overloaded, then the whole scale of where you're going to apply AI changes. So that whole realm of the human-machine interaction and the physiological interaction with the data is very tightly coupled. And that's why, as I said in my opening remarks, in a large-scale system, all these interactions are not very well understood, but you have to look at the whole system to be practical to use any of these approaches.
Yeah. And just follow up a little more. Getting back to cybersecurity, if we think of this, what we want this AI to do is not do tasks we do as humans. We don't, why is it that we're trying to get this thing to recognize images? Our vision systems work pretty well. We can recognize things. We want it to get to do the things we don't do well and concentrate on those. And in those cases, an explanation, it may not even make sense to us. We don't know how to solve the problem. Maybe there isn't an explanation that will help us to understand how the machine is solving the problem because somehow this is just beyond the way we think. But if we're careful to use these in ways that we understand what the outcome is. We may not understand how it got there, but we understand what the outcome is, how this applies, what it's telling us, and what it's not telling us. Not how it fails, but when it might fail. I think for many cases this is going to be sufficient. But that's also something we don't get out of today's systems, is a good understanding of when they're going to fail. And that, I think, is something, it's not quite the same as explanation, but I think that's something we need to concentrate on.
Did you want to follow up, Ashish?
Yeah, I have a quick comment. Transparency and explainability is an important area of AI, but what it boils down to essentially is explaining why a certain function or a certain set of equations solved by an AI system is behaving or giving such output, right? So the range, the amount of data that needs to be gathered and managed and then used for explainability of the system is going to be humongous. And we need to, as Paul pointed out, that we need to be careful about how we select those data points to explain them. And then, for example, GDPR as a compliance requirement has explainability as one of the requirements. How are you going to implement that? That's a big question.
Sanjay, did you have any response to this question?
Yeah, explanation is critical. Also, there's also the issue of checking. So one way to address that, I think, would be what you just raised. Would be to check the output of neural networks are inherently statistical. So they are making a decision now. Is there a way to validate that decision before you actually implement it? So if there is, then a few things can be done. That's one of the other stuff that we are exploring in our projects. But I think validation against some ground truth engine would be a critical part of deployment of an AI system for real world decision making.
So maybe before we go on to the next question, let me just point out that in the research field of AI, we have two types of goals that people focus on. One is to develop agents that behave rationally, and the other is to develop agents that behave like humans, right? So this stuff that Chris and Paul are referring to as the methods are augmenting people's abilities and hopefully helping them make better decisions more efficiently. Those are not always, the systems are not always built to try to replicate exactly what decisions humans would make, because that's much harder to put into the objective function. So it's worth thinking about as we start expecting certain kinds of behavior from our AI systems. So let's go on to the next question.
So it's a follow-up on actually getting AI to behave like humans or explainable AI.
Mm-hmm.
I'm sure you're aware of the, let me just take this so I don't have to lean. I'm sure you're aware of the dispute between statisticians and AI fans. So I'm just curious, what do you think are the transformational attributes that we still need to call AI intelligent? Because to a human, it's very difficult to also define what an intelligence is, especially when it takes like 10,000 pictures of a panda to know that it's a panda. But for a human, it's only one picture. You can tell the difference between a panda and a cat. So in your idea, what are the other transformational things that we need, or the big leaps that we need for AI to confidently say it's intelligent, it's behaving like a human?
Who wants to start with that question?
I'll start with that. I claim that we humans have too big an ego to ever accept that these artificial things are intelligent. So we will define intelligence in a way that these machines are not intelligent. And I don't think that is a bad thing. We've got lots of people. Let people do what they're good at, which is what we refer to as human intelligence. Let's get these machines solving problems that humans aren't good at. And let's look at this in the computer security domain. What are the things that we don't do well? And how can we use the machines to address those problems? Rather than trying to come up with machines that do a good job of doing what we already do well.
I'll sort of make an assertion here. So AI, as I said before, the taxonomy could mean a lot of different things. But if you say AI covers a lot of ground, everything from like simple single parameter rule sets like a thermostat, not a Nest, a thermostat. Then you have more complex rule sets. You have some automation. You have semantic processing. And eventually, at the far right of the spectrum, you'll have narrow AI and general AI, right? So then where does cognition actually kick in? Well, we have a Watson man sitting right here. So at what point do you query a Watson system that it becomes cognitive? So I assert that you could do a lot of things that one gets fooled into thinking it's AI, but it's nothing more than building a good ontology with a knowledge base and doing semantic queries. And then a system could very much look like an AI system because it gives you the right answers. But it's based on a knowledge base of well understood activities and performance of what you call the system. But it's when you get outside of those constraints into the unknown, that's when you run into where you need some more cognitive processing. But I'd say that maybe 90% of what we do don't quite fall into the cognitive area, but then become sophisticated rule sets. And I say that from my perspective, not some other domains, especially with these UAVs and autonomous vehicles. They very much look like AI systems, and they're full cognitive, and they do things that you wonder how they could react to the environment as they do. But they're very sophisticated rule sets. So semantic computing is one element of AI, and that answers a lot of the mail. But then to go all the way to the right side of the spectrum and then expect to do things like weed out cats and dogs and elephants and do it seamlessly, that requires a different technology that we don't quite have right now. So
I'll just add one more thing here. I
didn't mean to insult Watson, by the way.
No, I think Watson was a good stepping point for AI in 2011. Taking from psychology, intelligence is about learning from past behavior, or learning and generating more knowledge that can be useful to you or useful to others. Right? It's essentially about intelligence is all about learning. And whether you learn in a supervised manner, whether you learn in an unsupervised manner or semi-supervised manner is what we are looking at. And we humans do that. But as Professor Clifton and Paul have pointed out, and Professor Neville also pointed out that human-centered AI, like can AI help human beings to carry out tasks that human beings are not good at, right? And from that point of view, can we develop intelligence or AI-based algorithms and techniques that could help us become better in whatever we do or achieve as a society? So there's a lot of work going on in the industry about societal or AI for good, right? Societal good. And there is also work going on in the army side, right? Essentially military side. And the question is, how do you differentiate between what kind of algorithms you are using there, right? Or what kind of intelligence? That is where comes, are you using supervised learning versus unsupervised learning? Because if you start applying unsupervised learning in military side, it might become slowly get highly biased and cause harm, and that is where you need a human supervision. So, so intelligence might need to be administered and monitored by human beings at some level.
Well, I mean, there is a Turing test, right? So I mean, the distinction between human and machine intelligence can all be settled by the Turing test, right? So, I mean, do we really have to define what is human intelligence and what is AI? But there was an interesting article. I mean, we are very, very, very far away from human intelligence, recreating human intelligence artificially. There was an interesting article on natural language understanding by Douglas Hofstadter. Heard the name Douglas Hofstadter? He wrote this book called Gödel, Escher, Bach. He's actually at Indiana University, close by. Gödel, Escher, Bach. Anybody read that book? Yeah. Okay. Great.
Pulitzer Prize by computer science.
Yeah. Great. So he wrote an article, I believe, in the Atlantic magazine that despite all the advances in Google Translate and all, we are very far away from translating, things accurately. We can read novels and extract he gave lots of examples of, phrases and sentences that we can understand, but machines are nowhere close to understanding those things. So there's a lot of good problems to solve still.
Okay.
So I'm going to use nonlinear discontinuities as my stripper name. To go back to the original comment about healthcare and AI, it occurs to me that we've got a vast body of proved ground truth that AI could help explain to us. And I'm wondering if any of the panelists or if you, Professor, would have any thoughts on using AI to explain protein folding. If I put together a string of amino acids, in a millisecond, it's going to snap into exactly the right shape. We don't know how. I'm wondering if there's a way to, perhaps, Watson, model that process so that we could understand and have the AI explain to something that apparently is not accessible to normal human consciousness, even though we're doing it billions of times a second.
I was going to say, is Daisuke Kihara out here? We have people who are trying to do these things, trying to study it, very hard problems. And an interesting thing is, I think that's a very nice idea. Can we get the machines to explain to us how these things work? I think the first step, and we're not even there yet, is can the machines actually say this is what is happening or this is what happens without necessarily being able to explain to us? That would be a first step. Can they essentially predict what happens in these situations? That at least suggests there is an explanation in the space that the machines are capable of representing. And often we can at least describe mathematically what that is, even if we can't quite get our heads around any particular instance. And so I think there are ways we can use these techniques to better understand, but getting to the vision you have, I think, is still a long ways down the road.
So I have, let's see, it seems like we have a pattern if we're using MI like this. It's a nuclear pattern. So in the area of personalized healthcare, right? I mean, you're talking about a very tough problem. You talk about a problem that's like really hard, but we're sort of doing it. In personalized healthcare, we're doing a lot to understand using large data, big data analytics, and ML, and all the different techniques we can to understand proteomics and genomics and all the different omics to try to understand the onset of what the biomarkers are that indicate the onset of pandemics and endemics. So we have a whole group of people doing that, applying the same algorithms you do for radar missile defense. They're applying it to proteomics for personalized healthcare. It's a tough problem because clinical techniques now basically look at the general populations and look at symptoms, and doctors prescribe some medicine based on what they see across a large population. So the personalized healthcare takes an advantage of a lot of external data. It takes an advantage not just your blood tests and the blood assays. It's also taking into account your own genomics, your history, the neighborhood where you grew up in, and all these external factors to see what all comes together to give you the best course of action for medical care. So now if you're trying to unravel like the synthesis of how these things actually happen at a biochemical level, I mean, I don't know who's actually doing that, but the problem I was just defining is something we're approaching, and that's a tough problem in itself. So I think we're a long way off. But interesting question, though.
Shall we continue that pattern? All right. That's a great question. If you look at Watson Genomic Analytics project from IBM Research that worked on trying to provide assistive treatment techniques for cancer treatment. I was involved in that from security and privacy side point of view. It essentially what it does, trying to answer your question, is that it takes research publications about cancer treatment, about different corner cases of mutations, and trying to find out what could be a potential better treatment for a specific type of tumor. And that kind of issue is, and then there were a lot of false positives, and also it also saved, I think it saved some person's life, perhaps, I'm not sure that way to see, but it still is a product there, and it's doing a good job. So in the same line of work, perhaps when we want to explain protein folding, why that kind of phenomena works, right? We need to look at the underlying principles of the chemical formulation, biological formulation, as well as the atomic level of models. And the machine should learn that and reason about that. As it goes forward, then it can formulate the functions and the behavior of that in a mathematical manner. Then it can say, the protein folding is happening due to these reasons, right? And it can spit out many different reasons. So bottom line is the system should learn about underlying mathematical behavior of or develop formulation of those systems in a mathematically explainable manner, of the atoms, molecules, and their chemical properties. And that as a building block, then they can come up with explain these complex phenomena. I guess that is how we need to go, but we have a long way to go there.
So can I cut in and give you a chance to answer the next question first? So we'll get to, we've run out of time, so no pressure, but you'll be the very last question of the panel.
I hope I'm quick. In January 2007 or 2019, IBM came out with Initiative Q, and they were talking about the quantum computing. How does that work with the AI technology? I know that early theoretical papers from the 80s discussed that when quantum computing came on, AI would take off. And how do you see that impacting cybersecurity with the sheer computing power?
So Sanjay, do you want to take that first? I'm sorry I made that deal for you, but.
IBM released that quantum computing is out now with them. They're going to allow, eventually, this was obviously a press release that it existed, they're going to allow cloud-based quantum computing, but the ability for quantum computing speeds up calculations at such a huge angle. How does that impact with AI? Because now you already have a system that's making a huge amount of decisions and crunching a huge amount of data theoretically faster than we can. But there's also a new style of computing to go with it. Does that have an impact?
Okay, so I am very little idea of quantum computing. So, I would assume that it will have a huge impact. Yes, certainly large computing power, but maybe other folks.
So,
Can we change the pattern?
we are reversing
Lost.
it. So,
No, sorry.
Please.
No, I have an answer after you. No, you go. Go. Yeah.
So to answer your question, recently there was a paper that came out from MIT and IBM and other academic community members is that quantum is helping in certain type of algorithms where they're able to learn about patterns and essentially frequency mining or pattern mining, right? Now, the advantage there is that if you look at quantum computing, it is really good at modeling the natural behavior, natural phenomena, right? Essentially, I would say, from a classical computer is really good at modeling discrete behavior in the PNP space, okay, which are not NP but which in the P space. But quantum computing problems are moving from discrete to some form of continuous domain where it can address some of the NP problems, not NP hard, but some of the problems, right? As we move in the complexity theory from classical computers to quantum computers, right? Machine learning also has several similar type of problems, right? How do you learn about different patterns? And I believe it's going to help a lot in the domain of learning these patterns from continuous functions, okay? And if you look at cybersecurity, especially privacy. In fact, I was recently talking to someone about would privacy be impacted by quantum computing. In fact, we are working on a paper related to how quantum computing can help us determine data which are sensitive and not, and essentially privacy protection better. So I would, it's not a measure, it's just an academic work at this point. There's nothing, as a researcher, we are just dreaming about it, but we'll see how it goes.
So my response to that is, in the whole domain of transformational computing, which quantum is a part of, I mean, you can look at the processors. I don't think we talk much about the actual electronics and processors, but that's a big part of it. I mean, we couldn't do a lot of what we're doing today if it weren't for highly parallelized GPUs, or we're talking about neuromorphic processors or custom ASICs to just do AI functions. But it depends on what problem you're trying to solve. Now, if you're dealing with a cybersecurity problem distributed over large networks all over the world, you could design architecture so you make sure you place your sensors distributed also. So you're talking about computing at the edge and more the Internet of Things. And so you don't have a centralized processor. If you're trying to do a real-time problem, a quantum computer, you're going to need a data center to be able to host the problem and run your problem. But if you're trying to do something in real time or near real time, it's really highly dependent on the sensors you have available, what edge computing you have, and trying to pack as much CPU horsepower in the edge devices as possible to solve a different class of problems. That could probably be solved better that way than quantum, and quantum certainly, depending on the problem, could do better than a distributed cloud computing solution.
Okay, the last word, Chris.
I'll claim that fundamental problem in AI and the fundamental reason why we're seeing these big advances is not that we've been limited by our computing power. It's that we've been limited by the amount of data that we have to use to teach these systems, for these systems to learn from. Quantum computing is not going to change that inherently. And as pointed out, it'll speed up certain types of calculations. But I think the fundamental issues are how do we train these systems? What does it mean? And in particular, from a security point of view, how do we use these systems in a way that that are going to work in the light of a determined adversary who is going to try to find where the systems aren't working, what they aren't addressing. And I'm not certain that quantum is going to make a fundamental difference in dealing with that problem. For security, it'll make some fundamental differences in things like cryptography. These are going to be big issues for us in the security, but I feel that this is not our critical issue to think about. We've got much bigger issues to think about in how we want to take advantage of this technology to improve computer security.
Okay, that's our time for today. I'm sure the panelists will be up here for follow-up questions, but let's take this chance to thank them for sharing their views.